Hello, funny fanatki. Today we're going to talk about how AI image generators work. For example, Stable Diffusion.
Бу, испугался, не бойся, я друг, я...
So, quick recap. What is GAN? Generative Adversarial Networks. It's a method to generate image from random noise. We have a generator. It's the convolutional neural network that produces from random noise some image. After that, we have another deep convolutional network called discriminator. It takes for the input real image and generated one and decide whether the image is real or fake. So how the process of training is work? At first, both of them are bad. Generators generates random image. Discriminators update itself by not being able to guess correctly in the next iteration. So as the generator learns to generate from mistakes, it produces a good result at the end. We stop our training until both discriminator and human produce say that generated image is real. The main idea of GAN is to place two neural networks against each other. We can see an example of the generated images. All of them are non-existing people. So we can see that they're qualitative, but some of them have artifact. For example, this one and this one. So let's go further to Stable Diffusion. DALL-E, DALL-E 2, DALL-E 3, ImageGen, Stable Diffusion, Midjourney, all of them are diffusion models. Diffusion is simplifying the process to more intuitive way rather than GAN. What does it do? We call this process as forward. We decompose our transition from noise to image by step. It's hard to understand how to go from initial image to a noised one. Instead, we can do it with little steps. You can see it here. We add Gaussian noise for each time step. At the end, we get random noise. Since our Gaussian noise added together, we can skip some steps and produce noise at step T. So there's a question, how much noise to add and how much steps do we need? There's different approaches. Here you can see that we have 8 steps and we add the noise uniformly. One method is to add a little noise at beginning and set more at last step. Second one is to add uniformly. There are different tactics how to add noise, but this process is called schedule. When we're training, we can add different amount of noise to different image based on our schedule. In general, the number of time steps, it means how much we can divide our image by noise. We set in the range from 100 to 1000. So given a Gaussian noise, the model would require 1000 iterations to generate the result. What schedule to choose? In the DTPM paper, the author used a linear schedule. This means that the noise added at each time step was increased linearly. But in recent papers, by introducing new technique and different schedules, researchers could generate artistic images in as slow as t equal 4 time steps. So let's go to the next part of diffusion process. It's called backward. Our goal is to train network to denoise by steps. So if we can do it, we can begin with random noise and iteratively produce our initial image, like here, but in the reverse order. We'll use UNet as a network for training. For example, we take an image at time step 5. What we can produce here? Maybe it's initial image. Not, because it's difficult. We want to predict the noise that was added to the image. For example, here we predicted the noise, Gaussian noise from 0 to 5th step. Theoretically, if we removed predicted noise from our noised image, we'll get original one. But it's not perfect, because if we give noised image, it's some like wave shape. It has the shape of initial image, but it's noised. We try to make medium steps. What's the process? We take our noised image, we reduce predicted noise, and we get approximation of our initial image, which is actually less noised image. After that, we pass it to our next iteration and repeat it until we get our initial image, like here. So, due to iterative nature of the diffusion process, the training and generation process is generally more stable than GANs. Popular architecture to choose is UNet with attention, which is trained using MSE loss function in a supervised fashion. Why UNet? Ability to denoise and reconstruct the images efficiently by combining low-level and high-level features. UNet follow encoder and decoder structure, and additionally it have skip connection. Где-то мой чуть-чуть. Encoder receive input image and extract useful features using multiple convolutional layers. The decoder upsamples those features using transpose convolution and concatenate them with the process called skip connection. Skip connection skips some of the layers of neural network and feeds the output on the layer as the input to the next layer. It helps to transform the selected features from encoder to decoder part, which as a result helps to generate better noised image. Let's go to text to image. Text to image had a prompt which is encoded using text encoder, so we interpret the prompt. It guides image generator which uses diffusion to create the output. So how does the text influence the generation? First of all, for example, we want to give a muscular cat. First of all, we take our sentence, we simplify it to the root and remove some language constructions. We encode them as embeddings. The model also uses attention to account the context of the sentence. How does embeddings works? We can represent our embedding in the space of features. For example, for yellowness, we have action for yellowness, we have action for roundness, and etc. for other features. This is done using vectors. To simplify our space, we make similar, and to make similar object closer to each other, we reduce the dimension and place the image to latent space. What is latent space? It's abstract, compressed representation of original multidimensional space. How does the model know that strawberry caption looks like strawberry? It's trained on millions of images across the web that have captions describing what the image is. We have several numbers for images, we have encoding of the prompt, we have an image, and the model try with the experience to find a relationship between them. Let's use captions to train our model to find important features and relationship with one another. Additionally, captions in internet are not so detailed, so we create them using language models, for example, clip. Let's go further to our network. So how to condition our noise using embeddings? We take our prompt, make embedding from it, and pass it to UNet. We get some noise which is directed to our embedding. On the next step, we get the image which is likely connected with our prompt. To going through this iterative process, we'll get the image that's connected with prompt. How does it add to our UNet? It's added to attention layers. Here you can see them. So does this mean that with caption we'll achieve good results? No, the results are not so happy because they're not ideal. So how to improve it is to use classifier-free guidance. We have conditional noise predictor and unconditional one. Conditional connect with prompt. We get no embedded noise and embedded. When we subtract embedded from no embedded, we get some restricted noise that looks forward for our prompt. Why? Because we subtract part that is connected with prompt with random one. This can boost our noise to be more directed to the result. It's like a hack, but it's work. It's really targeting to where you want. One more question is why when we generate the picture from random noise, we get different images? Because the nature of Gaussian noise. It follows normal distribution, which gives a probability of where the pixels come from each step. And since it's probabilistic and not exact, we end up with different images than the initial one. This is how it works. That's all. Bye-bye.